start off, I'm not comfortable with a microphone in my hand, okay? I put my hands too much. So bear with me on this. This is new for me. Like I said, I'm just an ordinary guy here. I'm a chemist. I came out of the lab. I've been doing chemistry work for the last 18 plus years. Worked for EMB Millicor, which is probably one of the greatest companies you could work for. Division of Merck, KGaA, Darmstadt. So, I was under the impression I was going to be talking to chemists. Wrong assumption. Everybody in here, basically by show of hands, microbiologist? Do we have any chemistry people? Ah! You know what? I'm comfortable now. And I want to say thank you to Mark. You led into a lot of what we're talking about today, especially on the spectrophotometry side. My background is mainly chromatography, HPLC. But you can add the spectrophotometry in there. I didn't know 25 years ago that I would be standing in front of people talking about things that I just thought were just normal, everyday testing methods from a chemistry standpoint. And spectrophotometry was one of those methods that I used when I was in the laboratory. So let's move on, because I've got to compress this from about 45 minutes into 30. So it's going to be rapid fire for some of this. Some of it's going to be technical. For those of you that are chemists, you're going to understand some of this. Those that are microbiologists, you're still going to understand it because it's not hard. So, from a chemistry standpoint, let's move into the agenda. What is spectrophotometry? Why is it good chemistry and why does it work? What are ways that water is used? Very important, because water, if you think about it, is the #1 resource that we have today in this world. Wars are fought over water. That's how important water is. Various methods or instruments used for testing water. Efficiency of spectrophotometry. Spectrophotometry within the workflow, which in this instance it's in the food and beverage workflow. We're going to start from the beginning all the way to the end. Okay? Now, we're going to answer 3 at one time. And me being the way I am, I learn by visual. You can talk to me all day, but if I don't see a visual, I have a hard time understanding it. So what is spectrophotometry? Why is it good chemistry and why does it work? So, first one, what is spectrophotometry? Anybody heard of Beckman Coulter? Huge company, okay? A man by the name of Arnold J. Beckman and his colleagues, at that time called National Technology Laboratories, invented the first spectrophotometer. So this is basically some old technology now. I mean, it's 2014, so that makes it what? 64 years old? So it's been around a while, and like other methods, it's the same concept. You just may improve the technology a little bit, but it's still the same thing. You're using a light source, and you're using a detector, and we'll see that in a second. So spectro is a long word. Even I get tongue-tied trying to say it. It's a method used to measure how much of a chemical substance absorbs light by measuring the intensity of light as it passes through the solution. Okay. I move around a lot too, so let's look at this. You need a light source. You need a collimator, which is a lens. You need a monochromator, which is a prism. And your sample solution, your detector, and your digital display meter. So let's break this down just real quick from the technical source. Your light source, most of the time it's halogens, deuterium, maybe new technology, we're using xenon light. Doesn't burn out as quick. Like, kind of lasts forever. You know, I had to warm up an instrument for 20 minutes before you use it. And you have the lens, which is going to direct that light into the monochromator. And all we're talking about here is a prism. Every single chemical out there absorbs light. And guess what? You can identify that light, that chemical, by the absorption. But it only absorbs it at a certain wavelength. So you need the monochromator or the prism to take this light and break it up into the different wavelengths. What are the 2 types of light that we're talking about? We're talking about UV, which is ultraviolet, which you're not seeing. Starts about 185 and goes to 400 nanometers. Then we're talking about Vis light, which starts at about 400 nanometers and goes to 800 nanometers. That's what you see with your own eyes. You break it up, and you look for the specific wavelength in which that product absorbs light. Now all we're doing, let's say we have a piece of paper with a slit in it. We're moving this slit up and down in order to find the wavelength in which that light can pass through. Then we move it to your sample solution. And that adds a little bit more to the calculation of the whole thing, because it's how far does it travel through that sample solution. That's why we're going to show a visual real quick, because it helps me to help discuss this, or to teach. Then it goes to a detector and then a galvanometer, which is just a fancy saying of it's going to read whatever the results are of that. So why does spectrophotometry work? Why is it good chemistry? It's a simple chemistry, because everything absorbs light. But if you look at every chemical, they either absorb, they transmit, or they reflect light over a certain range of wavelength, which is what we just showed using the slit. Okay? Absorbance and concentration has a linear relationship. We'll explain that in just a second. The quantitative measurement of light absorption as a function of a wavelength can establish both the identity and the concentration. So I just repeated myself again on that. Here's where I go into the demonstration. Glass of water, cup of water. You put light through this cup of water. What's going to come out the other end? If this is pure water, it shouldn't absorb anything, should it? You should have light coming out this, shoot in this end, come out this end. 100% transmittance. That's what I'm showing here. 100% transmission. But as you go through it, transmittance doesn't give you a linear equation. You can look at the transmitted, but it doesn't necessarily tell you the concentration in a linear fashion. Okay? Let's add coffee. Hopefully it's cooled down enough and doesn't melt the cup. You put light through this on one side, what's going to come out the other? A little bit of light, correct? Just a little bit of light. Not as much. Now, why is that? It's absorbing the light as it goes through at whatever wavelength you're looking. Okay? Now, I won't hold these up. But let's say you increase the path length. Okay. This should be less than this. This should be less than this. And this should be less than both of those when it comes to transmittance. Which when you look at absorbance, this should be more than this should be more than this, and this should be more than this. And why is that? As light passes through, the pathway, the length of that pathway affects how much absorbs, or how many particles it's going to hit in there. Okay? Make it a little bit clearer? I hope it does. This is the one that we're concentrating on, is absorbance and concentration. Anybody heard of the Lambert Law? That's just a fancy way. It has nothing to do with drinking, because after drinking, you are not going to walk a linear line. Okay? The Lambert Law talks about if I have this much absorbent and this path length, the longer you get, it should correlate in a straight line. At this absorbent, you're going to have this much concentration. So let's say I have something that's at a 0.7. I should be able to come straight across without doing the calculation at this point and tell you what the concentration is. Whereas this one, I couldn't do that because it's transmittance. It doesn't calculate out the same way. Even though you could get the same result doing transmittance, the Lambert Law is what we're going to concentrate on with spectrophotometry. Oh man, you know what? I forgot to set the timer. So just let me know. Okay, ways that water is used. This is where it becomes more information. The technical part of this is over. There's a little over 7.2 billion people in the world today. We're talking food and beverage here, but if you look at how water is used within your industry, you can say, let's see if I can find it. Yeah, I like using my finger anyway. Drinking water. first of all, let's start with food and beverage. That's who we are. But there are about 1, 2, 3, 4 that can be related to the drinking water aspect here. And how is that? Well, let's start off right here, agriculture. What does it take to grow plants? Water. Okay, so we've gone to the agriculture, which that's what you're using in your industry is food, or food stuff to make whatever product you're making. Okay, that's going to people for consumption. Okay, processed water. Processed water is usually what's used within your facility. So, major part of the food and beverage. Then, what a lot of people don't think about this part, but you've got something coming in, you got something going out. Okay, it's just a simple. It's a law. Okay, not pure Lambert Law, but it's a law. So you have wastewater, so you've got to monitor what's coming out the back end. But what does that affect? That affects things like drinking water. Because this is all running into some place. So we have regulations for drinking water. So this is all related to each other in the whole food and beverage industry when it comes to water. And water is usually, like I said, it's the number one resource that you need. Nobody can survive without water. So what are various methods or instruments used for testing water, and how does that relate to the efficiency of spectrophotometry? Okay, on this slide I put a couple of instruments. Some of you may be familiar with these, some of you not so much. I did work in the micro lab for a few months or maybe a year when I was in the lab, and to me that's voodoo. I'm sorry. It's just messing with living organisms, and it may be this color if you give it this, or it may be this color if you do this, or it may grow on this. It is voodoo, okay? At least with chemicals, in theory, it's going to have the same reaction every time. So, I used this type of instrumentation when I was in the laboratory. But let's just go through some of the instruments that you can use. A photometer. Okay, we can go back to the very first. A spectrophotometer is made up of two things, a spectrometer and a photometer. Photometer is the easy part of it. You're just measuring the transmittance of light. That's all you're doing. Then you're sending to a filter how much transmitted. Okay? Amperometric titration. Big long word. Basically all you're using is current to do a titration of water. What are you looking for in that water at what current that you're using? It'll specify what chemical it is. Specific ion meter. Everybody has used a pH meter at some time in their life, and they've got the electrode. Okay? Well, they do make electrodes for specific ions, and that's all this is. If you're looking for a specific ion with the selector, you're dipping it in, it's giving you a reading, and once again, you're using a current of some sort. Inductively coupled plasma. You know what? I'm going to put that one. No, let's back up. Let's put those three in the same one. Actually, the inductive ICP and the atomic absorption. You're going down to the molecular level on these. All you're doing with this is you're putting some form of energy into whatever you're looking for, and you're exciting this atom, and you're getting the neutrons, the electrons and everything all excited, and they're bumping around, and you're trying to specify the ions on the ICP. And you have a detector selecting the specific ion you're looking for, whereas atomic absorption, you're basically going wham, giving it some kind of energy source, whether it be flame or whatever else they use for this, I can't even remember, but you're looking for electrons there. But the whole concept of that is you're exciting the molecule itself to give off either your electrons, your ion, or whatever you're doing, and you're specifying. Now, ion chromatography is more along the lines of what we did in our lab with HPLC. You can actually add the IC onto the unit. And what you do with this, it requires a mobile phase and a solid phase, something to carry it through for separation by ions. Then lastly, what we're discussing today is spectrophotometry. How does this compare to the rest of these as far as efficiency? Anybody having an ICP or just say an IC or an AA instrument in their lab? Pretty cheap stuff, isn't it? Anybody should be able to buy that stuff. But you're looking at these things, they're looking anywhere, a no-name brand at $30,000 to $100,000 plus for this instrumentation. Okay, now if you're a high throughput lab, go for it. It'll help. You can afford that because you're running through thousands of samples a day. But if you're not a high throughput lab, you need something that is reasonably priced, yet it's going to give you the same results as the other instrumentation does. What did I do? Okay, sorry about that. Efficiency of spectrophotometry. The easy button. Target. Cost versus benefits. Environment. Personal use. How does this all work together with spectrophotometry? Accurate and reliable results. And you said something earlier, Mark, that hits the spot on this. You may want to get as many results done in a day as possible to be most efficient that you can be, but guess what? If it's not accurate and reliable, it's just cost you even more money. And spectrophotometry can actually take a lot of that out, take the guesswork and the chances out of what you're doing, and still be accurate and reliable. Physical appearance. What do I mean by physical appearance? Small footprint, lightweight, and mobile. Go back to the ICP, the AA, the IC. And I can't remember who it was yesterday they talked. We was talking about it back there, I think, in the lab. When you're setting up a lab, room is that's a value in a lab. You need more space. And these types of instruments, the spectrophotometers, they don't take up a lot of lab space. Small footprint, maybe that big. We've got one on the table back there. Come back and look after the show, and we'll show you what it can do. But the other instruments, they take up large spaces in your lab where space is very valuable. They're mobile, they're lightweight. Did it again. Sorry about that. Ease of use. What's that? That's that microbiology going on up there. I'm telling you. Ease of use. Okay, I don't know about the microbiologist here, but the chemist can probably verify, vouch for me on this. When it comes to sample prep or doing a lot of the preparation work to either put it on an ICP or an IC or an AA instrument, it can be time consuming. Very time consuming. Methods aren't always that simple. Trying to get down to that level in which you can detect on those instrumentation. Think about it, spectrophotometry, you're just using light, which is natural anyway. You're putting in an instrument and using that to measure it. Simple methods. Minimal handling, that's a biggie. I know in the laboratory I worked in, we had a lot of technicians. Didn't necessarily have the background, so you wanted the most minimal handling that you could give them. And why is that? What happens when you have more handling? You get more errors, or you have more opportunity to introduce error into your testing. Cost effective. They're benchtop. I just said space was worth money in a laboratory. Handheld, you can move them basically anywhere within the facility that you're working. Safe and friendly. This is probably the biggest one over the last few years, is the friendliness to the environment and friendliness to the people using it. Environmentally, you want less waste, you want less packaging, you want less product which is used for the actual chemical testing introduced into the environment, because at the end you're going to see, you don't want a knock on the door after you've done all your testing and say, I'm from the EPA. We've checked your effluent water, and guess what? It's over the minimums. Over the maximums. Personally, anybody do ammonium testing? Maybe you're familiar with Nestler's reagent. Anybody heard of Nestler's reagent? Do you realize that's very toxic? And why is it toxic? Because the mercury used in there. You can't go dumping mercury. You don't want to handle mercury yourself, but you don't want to dump it into the environment either. And so a lot of these methods that you can do on spectrophotometry we reduce the toxic chemicals that you're using within the method. So you're not bringing harm to yourself or bringing harm to the environment. That's waste. Just went over that one. Okay, now let's move on to workflow. Wow. Now that's microbiology right there with all the colors. Okay. But let's look at 6 points of analytics in this. Disregard, I mean, we'll look at the green, but the one since we're in a hurry, let's look at drinking water, which is also part of the RO system, your raw materials, your in-process, your QC lab, and your effluent. First one, raw material control, which is, this is why I started on as a chemist. Unfortunately, I was in, not unfortunately, but fortunately I was within the pharmaceutical industry, so I had the FDA to tell me what I could do and what I couldn't do. I had to use the, just lost my train of thought. The Bible for some pharmaceuticals do raw material testing. USB testing. So I had a guidebook to go by. I'm sure there's guidebooks within the food and beverage also, but raw materials is where I started. So what parameters are we looking for? What chemicals are we looking for within the raw materials flow? They can be different from company to company. What's important to your company? What do you have the opportunity of introducing into your workflow that you may need to test? So parameters which often can be found, which I know is very important to the food and beverage, is disinfection or sanitization. Am I right there, Mark? Okay. So sanitization, disinfection parameters like chlorine, free chlorine, total chlorine, hydrogen peroxide, formaldehyde, all part of the disinfection program. Other parameters you can use within the raw material: iron, phosphate, nitrate, sulfate. I mean, it goes on. You're going to see total hardness throughout this whole process. Total hardness coming in, total hardness coming out is very important within a workflow. In-process control. Did this also. A lot of it was physical testing, but still did in-process control testing. Once again, just duplicate of the raw materials, but what parameters are important? What does your company deem important? Is it juice manufacturing? Is it a water bottling facility? Whatever your facility requires, both internally and externally. But once again, within this system, and why I keep bringing this up, disinfection parameters, we're adding 2 more on this one. Actually 3. But peracetic acid and ozone, along with the chlorine, and formaldehyde. And the reason I'm doing the workflow process like this is, if you've done the testing within the raw materials and you find no problem, then you move into the in-process. And let's say you're towards the end of that in-process, all of a sudden you do have a high reading in something. Well, you know it didn't come from the raw materials because you've already tested it. So you know it's somewhere within this flow of the process, okay? And I guess Steve brought it up to me, that's my counterpart back there. Basically, you're putting out a HACCP program. You're knowing within that process where the problems may occur or where they may not occur. And if it does occur, then I know I did it right here and I don't have to go all the way back here to test. So, what other parameters can you test for? COD. Now this one, the list goes on. These are just some of the ones that you can use. Ammonia, discuss that. What's the next one? How much time do I have? Okay. QC lab. What parameters, once again, can be different from lab to lab. What's important for your facility? These are the ones that you can, big ones that they do test for: ammonium, nitrate, nitrite, iron, phosphate, sulfate, and total hardness. Oh, and chlorine. You see chlorine a lot too. Why is that? It's a corrosive. You got to be careful what you put into the environment. R&D lab. I don't know if a lot of y'all do have an R&D lab. We'll just run through this one real quick. This one and the next one, since we are condensing it down, this will be rapid fire. Once again, but the R&D may be the one setting your parameters. They may be telling you what you're going to be testing during raw materials, what you're testing during your end process, and what you're testing for the final product. Iron, phosphate, ammonium, nitrate, sulfate, total hardness, chlorine. This one I think is very important, not from so much a standpoint of the environment, but money. within your laboratory, within your company. Just visited a customer down in Houston a few weeks ago with their boiler system. Went down. Guess what? It cost them per day over $300,000 because that instrument, that their cooling and boiler system went down. And it was by no fault of their own. It was because the instrumentation that they were using, they were starting at a zero that was up here where the baseline should have been down here. So when they were getting their results, guess what? They were already out of spec. Why did it cause this problem? Well, as you can see through the process, these are the steps needed in a system: clarifier, demineralizer, feed water, boiler. Then you go through the process, and then it comes back down. So you're going to a repetition there. So what can you test within this? And as you can see, you got calcium and all this. This is all part of the parameters we've discussed in the other parts of the workflow. But here's the reason why. You have scale. Effective scale. What is it? It acts as an insulator. Think of a pipe. That pipe gets smaller and smaller and smaller on the inside. What's it going to cause? You're going to have a pressure buildup. You're going to have friction. It decreases the efficiency. So you've got to shoot more energy or more fuel needed. What does it cause? Overheating. This damages equipment. That's exactly what happened to the facility down in Houston. What are the needs within this? Ultra pure boiling water, filtration, clarifier, soda lime, demineralizer, some kind of a resin. Corrosion is the second part of this equation. Most of the pipe and stuff within the boiler systems have a passivation layer, just a little coating to keep it from rusting or pitting or anything like that. But eventually wears out, and what you get is deterioration of the metal, which you weaken the structure with the pit formation and the rusting. What are the needs? Low levels of gases. And how do you get low levels of gases? You can do it by aeration, keep the water moving where it airs out, or you can have oxygen scavengers that go in and just Pac-Man the oxygen out of there, or the gases. Low levels of chloride and copper for corrosion. So you need corrosion inhibitors. The last part, which I think is very important and people don't look at, is the effluent factor, the back end of it. And this is the regulated part from my end, from a chemistry standpoint. I know the food and beverage is regulated, but now you're being regulated coming out your door from the EPA standpoint. And this is very important. This is where I say you don't want to knock on the door, because that usually means you're either shutting down or you're paying a whole lot of money. My example, when I was in lab, I had a very good chemist, but this chemist was like a bull in a china shop. She broke the chemist broke everything. Okay. At one time, she broke 4 thermometers in one fell swoop. And she wanted to hide it. So how did she hide it? Pushed it down the drain. Well, I got a call about a month later from the head of operations and said, "Hey, can you come to my office? We've got a problem. We've checked the effluent and the mercury levels are really high." How did this happen? So I had to go into the whole investigation. It cost us, I don't even know how much money to have somebody come in and do the cleanup on our effluent out the back end. So this is very important. It's getting even more important. So these are the parameters that you're checking for: COD, ammonium, nitrogen, phosphorus. The list goes on. But as you can see through this whole workflow, you can use spectrophotometry from beginning to end. Okay? Okay, closings and takeaways. Spectrophotometry is an accurate and reliable method, which it is, and it's an easy method. That's the whole deal. It's very monkey-proof. Not trying to, but that's how we want it. We want it to be able to just mix this, put this, push a button, and it's done. It's cost-effective and ensures the product is clean and safe for public use. When I say cost-effective, use that against the larger instrumentation that is used. Spectrophotometry, it's friendly and safe for the environment. It's a simple, easy method, and can be used within a majority of workflows within your environment at the company. Okay, since I've got to pay for myself, I've got to talk about my products just for a second, okay? Which can help you. From a food and beverage standpoint, we're not just chemistry. I mean, if you look at our table back here, we've got air monitoring, we have microbiology media, we have filtration. From the chemistry side, we do anything from visual test to quantitative analysis, things as easy as pH strips. Or let's say you just want a visual test. Is it there or not there for a paracetic acid? Dip it. Oh, it's there. Now let's go measure and see how much is in there. Or hydrogen peroxide. Then what my specialty is on the photometry side, the spectrophotometry side, which is instrumentation. But our catalog goes from A to Z. We can cover basically any aspect of testing within your lab, from test strips to instrumentation. It's a progression. How qualitative do you want to be? Test kits, reflectometry, handheld spectrophotometry for sanitization, for disinfection. You can walk around the plant with this instrument and do the testing. That's how simple it is. Once again, air monitoring, filtration, granulated media in a bag. How many of you have worked with microbiology media? And you open it up and you get this giant mushroom cloud. You do. I've dealt with it, and it sticks everywhere. It sticks to your balance and everything. Granulated media, try it one time. You don't have that excessive cloud. So I want to say thank you for allowing me to be here. I've enjoyed this. I hope I was not entertaining, but I hope you enjoyed what I had to say, and that it will help you whenever you're looking for efficiencies within your lab for chemistry. Okay? And I don't know if we have time for questions and answers or not.